The last set of notes for this unit are on titrations. A titration is a lab technique where a known solution is used to analyze an unknown solution. What's happening in a titration? Two solutions are going to react stoichiometrically. Hopefully, if you do the titration correctly, you can end your titration so that the reactants have reacted in stoichiometric amounts. In other words, no excess is left. A solution of known concentration and volume is added to a known volume of unknown concentration. If you know the concentration and volume of a solution, you can find the number of moles. If you know the mole ratio, then you can convert to moles of that unknown solution. And then you know moles and volume, you can find molarity. A couple definitions for titrations. Titrant is the solution of known concentration. A standard solution is also known as a titrant. It's also the solution of known concentration. So those are used interchangeably. Equivalence point is the point in a titration when exactly enough titrant has been added to exactly react with the unknown solution. In other words, it's the point at which the two reactants, usually acids and bases, have reacted in stoichiometric quantities. I say usually acids and bases because acids and acid-base titrations are what you're probably familiar with already, although titrations can be used for reactions called redox reactions, and it's the same purpose. You still use a known solution to find something out, usually concentration, about an unknown solution. An indicator is used in order for us to see when that equivalence point happens. And an indicator is a chemical that changes color at a particular pH. It's used to mark the end point of a titration. The end point is the point in the titration where the indicator changes color. Now, I feel like I'm kind of talking in circles here, but what you want to happen is when you have a titration, you want to choose an indicator that's going to change color at a particular pH range. Hopefully, that will change color at about the same point as the equivalence point. Because we can't see the acids and bases, we can't see when the moles have all reacted, we have to find something that will change color at about that same time. And so indicators do that. There are lots of different indicators. The indicator that you are probably most familiar with, and the one that's seen in this picture, is phenolphthalein, which turns pink when it becomes basic. Steps to solving titration problems. First, write the equation for the reaction. I would highly recommend writing the molecular equation for the reaction. I think that's easier. If you're asked for the net ionic equation, you can go to that later, but write the equation. Use the molarity and the volume to find the moles of the known solution. We'll multiply by the mole ratio to then solve for the moles of the unknown solution, and determine the molarity or the volume of the unknown given the moles, depending on what it's asking for. All right, so for example, what volume of a 0.1 molar HCl solution is needed to neutralize 25 milliliters of 0.35 molar NaOH? Let's see here, the first step is to write the equation. See here, HCl plus NaOH react in a 1-to-1 ratio, which is the important part here, to give us H2O and NaCl. We have a known concentration of NaOH and a known volume of NaOH, and we're looking for the volume of HCl that is needed to neutralize the NaOH. In other words, what volume is needed to react stoichiometrically. We're going to set this up using the molarity, 0.350 moles per 1 liter. We don't have 1 liter of the NaOH in this case, we have 0.025. liters. This lets us calculate the number of moles of NaOH that have been titrated here. I should label that NaOH, just so that we can see that our next step is to convert to moles of HCl. This is a 1-to-1 ratio, so the moles will be the same, but it's important that we show that 1-to-1 ratio step. This is 0.00875 moles, and we want to know what volume will give us that. If we start, I'm working backwards on my screen here. I hope you can follow this. This doesn't mean this is how you should do it, but there we go. So this is our molarity of the HCl, 0.1 mole per liter. This is the number of moles that we end up needing to titrate the NaOH. And so we can solve for x, x being the volume. So the volume would be in liters, 0.0875 liters would be our answer. Or 87.5 milliliters would be fine too. The next example has 28 milliliters of 0.250 molar HNO3, and then 53 milliliters of 0.320 molar KOH. And so we're asked to find the amount of water. So this one is a limiting reagent problem. There's another one where they're reacting in a 1-to-1 ratio. So at least that makes it a little bit easier. So what we need to do is we need to figure out how many moles of each one there are given the volumes. So, oh, I did that wrong, sorry. Hold on. I did that totally on purpose just to see if you're paying attention. It's 0.25 molar. Oops. Let's see if I can go back here. Sorry. That's 0.25 moles per 1 liter, but we don't have a liter. We have 0.028 liters of it. So that will tell us how many moles of HNO3 we have. And when you solve that, you get 0.007 moles. We're going to do the same thing with KOH. You set it up with the 0.320 over 1. You want to know how many moles there are in 0.053. And I can already tell you that this is not going to be limiting because your concentration is higher and the volume is higher and it's a 1-to-1 ratio. And indeed, when you solve this, you get 0.017 or so. So this is definitely the limiting reagent. We could continue this problem then to find out how many, the amount of water that's formed using that many moles of our limiting reagent. It's a 1-to-1 ratio, and then water has a mole weight of about 18.02 grams per mole. And that's probably not exact according to the periodic table, but I'm going to use it anyway because when you multiply that and round to 3 sig figs, I don't think it matters much. So you get 0.126 grams of water. The last example has 0.5 molar calcium hydroxide. We want to know how much, what volume of that is needed to titrate this volume and concentration of HNO3. This one is slightly different because it is not a 1-to-1 ratio because calcium hydroxide has 2 OHs. We'll need a 2 in the water and a 2 out in front of the nitric acid, which means we need twice as many moles of nitric acid to titrate the CaOH2, or we need half as much calcium hydroxide to titrate the nitric acid. So again, whenever you see that capital M, I would convert that to moles per liter. We're solving for 22.2 or milliliters, or 0.0222 liters. At 0.0365 moles, and this is of the HNO3. In order to convert to calcium hydroxide, we need to multiply by 1/2. And I would label that, but it's going to go off the screen. So I will just say that this is 0.01776 moles of calcium hydroxide. And we want to know what volume it will take to get that if we have 0.5 molar. So once you do that, you end up limited by the 0.5 molar in terms of sig figs. Only one sig fig, 0.04 liters is what you would need. So I know this is a little bit longer and a lot of me talking through examples. We'll be doing some more examples in class, but hopefully this will give you an idea of how to start those.